Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. Hi, everyone. It's my great pleasure to introduce David Molnar, who is going to talk about RFID security and security testing. So, this is David.
Right. Thank you very much, Patrice. It is my pleasure today to talk to you about two areas of computer security that example the different range of approaches we need to make progress in the area. So the first thing I want to talk to you is about RFID. And to do that, of course, I have to tell you what it is. So RFID is a term that refers to a range of technologies where a small computer with an antenna called a tag is attached to a person, an item, or a collection of items. And then a different computer called the reader is able to talk to this little tag and ask it for the information it carries. And in many cases, and the cases I'll be talking about in this talk, the power comes strictly from the radio waves of the reader. There's no battery to change, nothing to wear out, and this is what makes it very attractive for the sort of identification space. So the interesting thing about RFID is the applications are everywhere. This slide just shows a few of them. So you can see here on the top we have Fast Track. That's sort of the California automatic toll payment system. You see credit cards on the top right where the credit card sends your credit card number wirelessly over the air to a reader as it comes in. On the bottom right, you have library books with RFID tags on them, which I will talk about. And of course, your driver's licenses here in Washington now have the option of the so-called enhanced driver's license, which includes an RFID tag. And even United States passports now include these devices, which I will also talk about. But one of the key problems of these devices is that what are the security and privacy implications of using them?
Is this Assemblywoman Fran Pavley? Or is this her? The card reader that restricts access to the state capitol says it's this gentleman.
I was Ms. Pavley.
Jonathan Westhuse is really a security consultant hired by State Senator Joe Simidian.
It's my own design.
With a homemade antenna and a laptop, Westhuse was able to read radio waves emitted by Pavley's identity card, duplicate it, and then gain access to a secured area of the state capitol.
All that was done within a moments of time without me even being aware of it.
Simidian's experiment illustrated just how easy it is for a hacker to read those radio frequency identification cards, or RFIDs, from a few feet away.
If you can read someone's information and then literally in a matter of seconds clone their card and pass yourself off as them, imagine the mischief that people can do.
So what this shows is that people use these devices believing that they have certain security properties when in fact they don't. And anyone with some basic electrical engineering knowledge can come along and build something that defeats the security of the system. One of the things that makes it difficult to design around these security issues is that, as I said, RFID is a range of technologies. On the one hand, you have things like the chips which are used in US passports. They cover a lot of information up to and including a digital photograph of you. And they can do a lot of computation up to including RSA signatures. On the other hand, you have devices used for Walmart, originally designed for tracking tubes of toothpaste, which are now in enhanced driver's licenses and the so-called pass card, which are nothing more than a sort of long-range readable barcode. They can be read at sort of 5 to 10 meters, but don't really have much in the way of computation. So what I did as part of my work was take a look at some real deployments to understand what are the security and privacy issues and how can we come up with new methods of addressing these problems. So the first deployment I want to talk to you about is library RFID. So the San Francisco and Berkeley public libraries were considering spending millions of dollars on RFID tags for every single book in the library. $1 per book, 1 million books, $1 million of public funds. The payoff is that these tags enable easy self-checkout. You can walk up to a kiosk, wave the book over the kiosk, and automatically figures out who you are, what the book is, and checks you out. Or, as you can see in the picture, when you walk out the library door, you walk through these gates, the gates read all the books in your backpack, and if you haven't checked one of them out, it reminds you that perhaps you need to do that. So there were actually huge public concerns, people coming up to open meetings, people coming to library trustee meetings about, well, what is on these tags, who can read them, and from how far? So I was able to serve as a pro bono consultant for this Berkeley Public Library. I volunteered my expertise as a computer scientist to help them understand these issues. And in return, they actually let me ask vendors, so what do you really do? Tell me. And they had to answer. It was great. So one of the things I discovered was that some vendors actually advocated putting the title and author of the book on the tag. And what's more, these tags could be read by anyone with a compatible reader. So that leads to an immediate privacy concern of someone being able to scan you as you walk through these gates or anywhere like that and learn exactly what you're reading. And it turns out there's a long history of people being very concerned about what you read, and other people wanting to not reveal that information to just anyone who might be passing by. But then we looked a little bit deeper and said, okay, what if you get rid of this title and author? Well, a lot of different places also suggested putting the barcode, the library barcode, on the RFID tag. And this is sort of a static, unique identifier that never changes. And one of the things we discovered was this attack we call hot listing. Suppose you're interested in a specific book in the library. For example, the FBI circulated a memo to its agents in late 2003 saying, be on the lookout for people with almanacs, because we believe they are using almanacs to plan an attack on the United States. You can't make this up. I can go to a library that uses RFID, like the Cesar Chavez Public Library branch in Oakland, and look at the tags, discover the barcode for the almanacs, and now, because it's a static, unique identifier that never changes, every time I see that particular barcode in the future, I know it's from Oakland, and I know it's the Quran or an almanac or what have you. So one of the things we did then is say, okay, let's work to figure out if there's some new cryptography we could use or some new different methods we could use to change these IDs every time. And then we ran into this sort of systems problem of the actual collision avoidance protocols used by the ISO 15693 tags baked in unique tag identifiers to the collision avoidance behavior of the radio protocol. And by looking at the collision avoidance behavior, you could just find out what tag it was, even if at the data level you were rewriting it every time. So our contribution there was to sort of realize the full sort of vertically integrated systems problem. I then moved on to electronic passports. So the proposed, yes?
Before you move on to passports, was there a solution for that? Or?
I'll talk about some cryptography we came up as a partial solution for that. And since then, there have been new air interface protocols which don't have the same problems that we talked about. Does that answer your question? So the next deployment I want to talk to you about is passports. So here, remember I said that passports are sort of on the other end of the spectrum of computation. A digital passport includes your name, your passport number, a photograph of you, and your nationality. So if you take a look at your passport, you have all this information here on the front cover, like your picture, name, passport number, so on and so forth. All of that is on the chip inside the passport. For instance, my passport, I can tell by looking at this small symbol, actually has the chip inside of it. The original deployment choices of the United States included no encryption or authentication of the chip. So anyone with a compatible reader could go up to your passport and say, excuse me, I'd like to know who you are. And the passport would send all of this over to the reader. Yes?
They allege that it has a Faraday cage in the cover. Does it or does it not? Because a closed passport is a fairly good Faraday cage if it's made of metal.
So the question is there a Faraday cage in the cover? And the answer is there is now. There was not in the original deployment choices. So I'm talking about back in 2005 when we started looking at this, the United States State Department published what they call a concept of operations, where he said this is what we're going to do. And the Faraday cage was not part of that concept. Does that answer your question? So the key problems with this original deployment choices are, well, first of all, there's a privacy issue. If someone comes up and reads your passport, they know who you are, even if you didn't want to tell them. But there's actually a more serious issue. The more serious issue is that because it didn't check whether or not the information was coming from a real passport or from a small homemade device like the one you saw Jonathan Westhuse made, what this means is that if I scan your passport, I can pretend that I'm using your passport in anything that uses an automatic sort of use of the passport. For example, Australia trialed gates, which would swipe your passport and do face recognition to figure out if you're allowed in the country or not. So I notice here you have these nice gates at the entry to Microsoft Research.
We do that.
Yeah. So imagine coming back to your home country, swiping your passport, and then having a camera look at your face, look at your passport's picture that's presented, and say, oh, is this the right person or not? Because the original choices didn't actually check whether the information was coming from a real passport or not, I could try to use your passport. And the reason this is important is because it lets me try to imitate your face at home instead of at the border. So I can go scan someone who looks somewhat like me and then figure out what the correct Polaroid to hold up to the camera is at home, or facial prosthetics or what have you. But the point is that because the biometrics are coming from the passport and it didn't authenticate the chip, yes?
So you're saying there was some kind of cryptographic signature that paired the identifying information with the face, so you could just replace the picture and then show up and it looks like you.
Yeah, so the question is, was there a cryptographic signature that made sure that I couldn't just replace the identifying information directly? And the answer is yes. There's something called passive authentication where the issuing nation signs the information. We've recently learned that no one checks those signatures. But that was not part of my work. And then the final thing, of course, is this. This was reveals a nationality, and so it's a U.S. citizen detector, which might be bad. So what we did is we wrote this down. We submitted a formal comment to the State Department with the Electronic Frontier Foundation. 2,400 other people sent in negative comments about these choices. And there was public outcry, demonstrations, what have you. So the State Department ended up adding encryption to e-passports. Now, whenever we have encryption, of course, a key question is, where do you get the key used for the encryption? And the answer is, the key is actually derived from information that's right here on the front cover of the passport. When you go to the airport, as I did in San Francisco International before coming here, you either swipe your passport or have it scanned, and then the machine gets this key, authenticates to the passport, and obtains the information. This works for the passport workflow where you're already giving your passport to somebody. But it doesn't work for other RFID applications, where the whole point of radio frequency and remote reads is to not touch things. Yes?
It does work for the passport, but now that you have to expose it over the passport, what does an RFID do that the 2D barcode would not do?
Why wouldn't you just read the information directly?
So the question is, what does the RFID do that the 2D barcode does not do? And the answer is, in the particular choices they ended up with, there's no difference. But there is an optional feature not yet implemented where the chip would do a challenge response protocol to prove it was an actual chip made in an actual passport facility. This is called active authentication. It is an optional feature. It has not been implemented in the current US passports to my knowledge. Does that answer your question? Does that answer your question? Yes?
That doesn't answer my question. Now, what does that do to the digital signature, doesn't it?
Well, the active authentication would actually authenticate the specific chip, not just the actual digital, not just the information on it.
Couldn't you just sign, as part of the signature, include the chip ID?
Well, how would you authenticate a particular chip has that specific ID?
Okay.
Does that answer your question? Okay.
So it's a cloning issue.
Yeah, it's a cloning issue. So the question was, what does why would a challenge response do something different from just signing the information on the passport? And the answer I gave is that it's a question about trying to prevent cloning of the actual chip involved. But the point I'm trying to make here is that we found a solution here for this problem that integrates with the workflow of actual passports, but what are we going to do for other RFID deployments? And if you think about it, there's an underlying theoretical problem here. And it's a problem I like to call scalable private authentication. So here you see Alice talking to one of two different RFID devices. And you see an adversary listening in on them. And I'm going to show you a protocol which solves the problem of private authentication. That is, Alice should be able to authenticate to the chip and vice versa without the adversary knowing which tag is being read by Alice. I want to talk about solutions for a subclass of all the tags we have where we can do some cryptography. So the solutions I'll talk about will cover some of the RFID devices in existence, but not all. And I'll argue there's still some interesting problems to solve even in this class of devices, where we're allowed to share keys between Alice and the tags, and where we're allowed to do a little bit of cryptography. So the first protocol I want to show you is a protocol where Alice and the tag share a secret key. Alice begins by creating a random nonce, a 32-bit value that never repeats, sends it to the tag creates its own nonce, and it evaluates a pseudorandom function on the shared key in the two nonces. And just to briefly argue why this gives us some nice properties, an adversary who doesn't know this shared key won't be able to predict what the proper value is to respond as the tag, and so won't be able to impersonate a particular tag. By the same token, because this is a pseudorandom function, without knowing the secret keys of different tags, the adversary won't be able to figure out whether a particular response came from tag A or tag B. And the only problem here is now scaling. So in this picture, Alice and the tag share a key, and they both know they share a key. What happens when a new tag shows up in Alice's field of vision that she's never seen before? Well, the naive thing to do is Alice needs to try a different key for each tag it could possibly be until she succeeds. So that scales linearly as the number of tags scales. And the question is, can we do better? So let me show you something, an attempt to do better that doesn't actually work. So the attempt is this. Let's give every key a unique identifier, have the tag simply say, I'm using key number 5, and then Alice has no problem with scaling. She just looks up key number 5 in some hash table and says, OK, this is the key I want to use. Great. And we run the protocol, or any other authenticated key exchange, or any other protocol that you happen to like. But the problem with this is that it breaks our privacy guarantees. Again, we have a unique static identifier for every tag. And the question now is, what can we do? If the tag sends anything that's correlated with its identity, it seems like the adversary will get an idea of which tag it is, which breaks our privacy guarantee. But if we don't, then Alice doesn't know which key to use, which breaks our scaling problem. So my solution to this is to use a so-called tree of secrets. Alice knows every single secret key in this tree. Each tag is associated with a leaf in this tree and knows the secrets on the path from the root to the leaf. So this particular picture, you have a tag on a library book, and it knows the right secret, then the left secret, then the left secret. And what we do in order to authenticate and identify a particular tag is the following. We start out using the protocol I showed you and say, OK, am I in the left subtree or the right subtree? Which of these two keys do I share? So we can use the protocol I showed you, which scales linearly in the number of possible keys. But there's only two keys here, just the left key and the right key. And Alice and the tag can figure out which one they share and then walk down to the right subtree, while an adversary who's listening in has no idea where they are. Similarly, they can do the same thing, left subtree or right subtree, and go on and so forth until they reach a leaf and they discover, yes?
What if the adversary is the neighbor at the bottom of the tree?
So the question is, what if the adversary is a neighbor at the bottom of the tree? And that's a question about sort of tags sharing keys. For right now, I'm talking about an adversary that's sort of a radio-only adversary. And in order to mitigate, and I'll get to this question in just a second. So for a radio-only adversary, the adversary can't tell anything about which tag it is. And we get scaling that's logarithmic in the number of tags. Now, Stuart's question is, what if the adversary happens to be one of the neighboring tags? Like, suppose you've broken into one of these tags and extracted secret keys. In that case, it's an interesting question about trading off privacy for efficiency that other people have actually followed up on my original work and looked at. Well, in particular, you don't need a fully branching binary tree. You can actually have a larger branching factor, or even different branching factors at different parts of the tree. So there's a very nice paper at PETS 2006, which talks about how to make the trade-offs based on how many tags you think will be broken into and different efficiency metrics you might have, such as the amount of communication or amount of computation for the reader. Does that answer your question, Stuart?
Okay.
Other questions so far? So what I want to show you on this slide is a comparison, just a simple comparison between the asymptotics and then the actual concrete numbers for a back of the envelope implementation of the scheme for 2 to the 20 or 1 million tags. So you can see here that it scales better than the sort of naive scheme of trying every tag in turn, but also scales better than a scheme where you try to do some pre-computation ahead of time and treat it as sort of a key cracking problem and do like a trade-off, time-space trade-off. But here at the bottom, we have, like, again, concrete numbers for the reader time, reader space, space and communication for the tag and for the reader. Just to give you some idea of how we could actually make this work in an actual implementation. So the sort of thing I want to leave you with from this part of the talk and this particular project is this is a story where we start off by looking at practice. Real deployments of RFID. We discovered there was a fundamental problem, private authentication and scaling private authentication. And then we needed to come up with a new algorithm to solve this problem, which I've just showed you. I want to change directions now to talk about some of the work I did while I was an intern here at Microsoft. And that's in software security, looking for serious bugs. Now, as I'm sure people here are all familiar with, these bugs are quite common. And in fact, if you take a look at this URL, you can go to the Computer Emergency Response Team statistics and look at how many bugs were in 2007 or how many bugs were in April of your favorite year. Well, in 2007, there were 6,515 such bugs reported. All major vendors, Apple, Adobe, Microsoft, many others. And as you probably know, for each bug, writing a patch, queuing a patch, and releasing is very costly. So we'd like to figure out a way to have fewer of these bugs and mitigate these bugs as early as possible. The way I like to think about sort of work in this general area is there's sort of a bug cycle. We start off where we write a bug. We don't really mean to write a bug, but we do. And then we find a bug, or more likely someone else finds a bug. We have the bug reported to us. We try to fix the bug, and then we write another bug. So there's a lot of work on how not to write bugs in the first place.
You make a lot of money with it. It's beautiful.
It's wonderful, yeah. So there is a lot of work on how not to write bugs in the first place. And if you can do that, you should, obviously. But but sometimes we don't have that luxury. And sometimes we have legacy code or we have other things that prevent us from using techniques to not write bugs in the first place. So my work that I'm going to talk to you about has been focused here on this sort of finding bugs and reporting them part of the cycle. And that's work I did here with Patrice and Michael Levin when I was an intern here at Microsoft Research. And I've continued to do back at the University of California at Berkeley. So the jumping off point for this work is a classical technique called fuzz testing, whose story actually does begin on a dark and stormy night in the middle of Madison, Wisconsin. Professor Bart Miller at the University of Wisconsin-Madison is dialing into the modem pool, and he notices that the line noise from the storm is causing his utilities to crash. So he realizes that what nature can do by chance, man can do by design. And he gets 2 of his graduate students to write a line noise generator for his favorite Unix utilities. And it finds lots of bugs. So today, one implementation of this basic idea is the following. You pick a seed file. Where you get the seed file from is up to you. You can get it from Bartlett's familiar quotations. You can generate it purely at random. Or you can have some other heuristics to generate it. Then you take random bytes, here highlighted in red, change them some other random bytes, feed it to your program, and say, oh, does it crash or does it not crash? So this is a very simple, very sort of straightforward way of testing a program. Miller himself refers to fuzz testing as sticks and stones kind of testing, but it's remarkably effective. So from their original paper, they found between 1/4 to 1/3 of all the Unix utilities and binutils crash, depending on the particular version of Unix they looked at. And of course, the Microsoft security development lifecycle now requires 100,000 fuzzed files before releasing any software to the wild. And I can give you many, many more anecdotal reports of fuzz testing's remarkable effectiveness at finding high-value security bugs. But the problem with this particular approach is it doesn't handle unlikely paths. Here's a small piece of code, which I hope none of us will ever write for real. It simply compares the very first character of the input to B and crashes if it's equal. And as you can see, if you're just randomly testing, you have a very low chance of hitting this particular bug. So the fix is something called Whitebox fuzz testing that I worked on here, which combines this idea of fuzz testing with this idea of dynamic test generation. So let me now tell you what is dynamic test generation. So in dynamic test generation, we trace the dynamic execution of your favorite program. We capture a symbolic path condition, predicates about the input that have to be true to go down this path. We then pick a new path we want to explore and come up with a new symbolic formula for that path. We have a constraint solver, which tries to solve this new path condition. If it can solve the new path condition, we extract a new input from the result and run the program, thereby expanding the coverage of the program that we've tested. So this was originally developed by a sort of a pair of seminal papers, one by Godefroy, Clarland, and Sen, other by Kadar and Engler. And the idea of using sort of symbolic execution goes back to sort of static test generation ideas as far back as King in 1976. So let me now show you this idea in practice on this particular small program. So this is a program we had before. It simply compares the first input to B and crashes if it's equal. Let's run it on the input good, see what happens. Well, if we run on this particular input, we come up with a path constraint that says, okay, the first letter of the input is not equal to B. That's the one predicate we tested on the input to go down this particular path. We want to come up with a new path through the program. There's really only one logical choice. It's to take the other direction of the if statement. So we negate this path condition. And then we feed this to our tame constraint solver in the corner. We ask the constraint solver to find a new input that satisfies this constraint. The constraint solver says, OK, I have one for you. Bood. We run the program, and then it crashes. So we've now overcome the unlikely paths problem. Yes?
Well, I'm just concerned about the constraint solver's ability to find ways to get to all paths. This ultimately is the halting problem, I guess.
Right, so the question is, isn't this the halting problem? And the answer is yes, finding all paths is difficult, which is why we end up in this regime where it turns out empirically constraint solver does very well on many of the paths we want to solve for. Why it does very well is an interesting research question, and that's something that I actually have an undergraduate working on at the moment who's trying to characterize some of the reasons why that might be true. For example, in the tool I built at Berkeley, which uses the constraint solver STP, 70% of the time we call a constraint solver, it returns in under a second with an answer. And so we're trying to figure out what is it about real programs that leads to that. So this also touches on so Josh's question also touches on this other issue of scale, right? So the first generation tools are extremely exciting, but they looked at sort of smaller programs. And the question now is, how can we scale them up to larger programs? Maybe the constraint solver will fall over. Maybe we don't know how to instrument large programs. I think there's some other questions that come up, but I want to focus on the search strategy question. And I'm going to argue that the depth-first search approach, which the early tools used, doesn't let them scale as much as we would like. So here's a slightly more complicated program. And you can see here we've run the input good again. We've come up with these 4 predicates that it generates for us as the path condition. And now the question is, OK, we have a much larger program search space than even the small program I just showed you. What do we do to search? Well, the initial choice is, very natural initial choice is just use depth-first search. We'll take the last condition, we'll negate it, go down this path, and then symbolically re-execute the entire program with the new input. And continue doing this over and over and over again. So we keep symbolically re-executing and then doing a depth-first search. Now, the reason this is particularly unfortunate in large programs is just the way the economics work out is this. For a typical program that's very large, you might have the time to create a symbolic trace be 25 minutes. There might be thousands of path conditions or thousands of predicates in that path condition, each one corresponding to a different if statement or a different branch you could try to go down. And the time for each branch to solve, generate a new test case, and check that test case for crashes is about a second. So what we want to do is amortize the expensive work of generating these path conditions over many new test cases. And the reason for that is each test case is a bite at the apple. Each test case is an opportunity to find a new bug that will justify all the hard work we've done so far. And so we had to come up with a new search strategy that lets us do this. The answer is something called a generational search. So in generational search, you see the initial path taken, good. And what happens is we generate each of the test cases we can get to by flipping one of the predicates in the path condition. And so we get sort of 4 test cases in this example instead of just 1. And you see the sort of set of test cases we generate here at the bottom. We call these generation 1 test cases. The seed file is generation 0. We generate generation 1 test cases. And then, of course, we can re-execute on any of those to get generation 2 test cases, generation 3, and so on and so forth. The overall search space for the program now looks like this. So let me tell you what you're looking at here. On the bottom, you see the actual test cases generated by this technique. Above them, you see a number, which represents the generation of that test case. And then the bomb represents test cases that actually crash. So after only 3 generations, 3 symbolic executions, you end up hitting different test cases that crash, instead of with the depth first search having to walk all the way from left to right through the search space. Yes?
But again, you're very trace dependent, right? So, and that's a big part of what the overhead is.
So the question is, we're very trace dependent, and isn't that a big part of the overhead? And the answer is yes, we are trace dependent, but we manage to get lots of different test cases from each trace. And that's one of the things that makes this search strategy better than the previous search strategies that were employed. Does that answer your question?
Yes, but I'm just wondering that, I mean, it's the same thing with profile-based optimization. You cover a very small part of the program. So if you don't come close to kind of, if the bad parts of the program are in cases where you don't even have a good trace through it, you won't find them.
Right, so the question is, what happens if there's a part of the program we don't even have a trace that's nearby it? What happens then? And the answer, I would say, is that that's where the art in picking the seed files comes in, for example. Or trying to figure out if there are parts of the program you haven't covered yet that you need to direct the technique towards. Does that answer your question? So one of the things I worked on while I was here is this idea of active property checking. So the basic technique I just showed you looks at code coverage. We came up with new paths that cover new parts of the code that haven't been tested yet. But of course, there are security bugs that don't actually show up in the path condition. For example, you might observe that there is a buffer, and the index depends on the input in a way we can reason about. And we would like to know if that index can ever be outside the bounds of the buffer. Or we might know, because perhaps someone has given us a SAL annotation that says this particular parameter should never be null to this particular function. We would like to know if we can solve for an input that makes that parameter null. Or maybe we have a division, and the denominator depends on the particular input. We want to see, can we solve for division by 0? So I worked on ways to sort of check many properties simultaneously. And the way I like to talk about this now is sort of dividing the solver queries into sort of 2 types. One type is coverage seeking, where we're looking for new inputs that increase our coverage of the state space and coverage of the program. But the others are sort of bug seeking, where we say, OK, I'm going to solve for a bug and see what happens. I want to talk to you about one particular type of bug that I think is a really great fit for this technique, and where I've had to develop some new methods to look for this kind of bug. And that bug is integer overflow, integer underflow, and other integer bugs. These are bugs that come out because programmers believe machine arithmetic is unbounded and works just like the arithmetic we all learned in school. It doesn't. And what happens is that it leads to these subtle bugs that can really confound our traditional approaches to find security flaws. So for example, one of the traditional things that we do is use stack analysis. But reasoning precisely about the values of integer variables is hard, which leads to many false positives and leads to programmers turning off the tool. There's a humorous quote from Linus Torvalds about GCC's attempt at finding such bugs in 2001, where he refers to so broken it's not even funny. Now, we've made a lot of progress since then, but it's still a fundamental issue. Another approach that we often use in security is to have a runtime monitor that looks for unsafe behavior and then terminates the program if it looks like we're doing something not safe. But the problem here is that there are benign integer overflows. Some code in cryptography, for instance, might use integer overflows to do a very fast modular reduction. If you terminate the program when that kind of overflow happens, you'll make a very angry user. In contrast, we can use ideas about these bugs to direct our search and only report test cases generated that are real serious bugs. So in slogan form, stack analysis wastes a programmer's time. Runtime analysis wastes the user's time, but using it for dynamic test generation and whitebox fuzzing only wastes the tool's time. And at 10 cents an hour for the tool's time versus more than 10 cents an hour for my time, I know which one I'd rather use. So this is a particular kind of bug. This is a piece of code that you might write if you were trying to bounds check this integer x before passing it to copy bytes. Unfortunately for me, this particular integer is signed. And if x is equal to -1, then it will pass the bounds check. But this copy bytes has a prototype which says it's an unsigned integer. So when I pass -1 into this particular function, it will be promoted to an unsigned integer. And we're going to copy a few more than 800 bytes. So the bug pattern here is we're treating the same value as signed and then as unsigned, or vice versa. So the way I like to think about this is by having sort of a 4-point lattice of types. Every value in the program starts out as unknown. We don't know if it's signed or unsigned. If we see it as an argument to a signed comparison or unsigned comparison, then we can give it a type. And if we see it as an argument to both, one after the other, then we can move it to this bottom value, which indicates a potential bug. The way that interacts with the technique I've talked to you about so far is that if you see a tainted program value, a program value you can reason about that has this type bottom, you can solve for an input that will make that equal to -1. Why -1? Because that will exhibit the difference between signed and unsigned comparison. And so what I developed are methods to infer these types in a memory-efficient way over very long traces. Because it turns out, as I'll show you in a few slides, the traces with which we deal are several hundreds of millions of instructions long. So my first attempts at inferring these types automatically were not memory efficient in the size of the trace. And so I ended up running out of memory on real programs. So I developed a method which attempts to have a very small amount of memory in order to keep track of only the live variables at each point of the program that might have different types. So if you put this all together, the architecture looks something like this. You come up with an initial input, you check it for crashes, then you trace the program on that particular input, you gather some constraints for your constraint solver, you solve the constraints, you get a whole bunch of new inputs, and you move on and repeat the cycle. So I've been privileged to be involved in sort of two different systems that do this. One is Sage here at Microsoft, and the other one is called SmartFuzz. It's what I wrote at the University of California, Berkeley. And I want to sort of share with you some of the initial experiences that we've had. So Sage was originally released internally in Microsoft in April 2007, and since then found dozens of new security bugs, which had been missed by black box fuzzing, static analysis, and human code review. It's bugs that, if they had been found externally to Microsoft, would have resulted in a security fix. And you can see here that there's been a number of people who've worked on Sage showing the amount of investment that Microsoft has put into it. I want to show you an example of such a bug. So this is a bug in animated icon parsing. Some of you may be familiar with this bug already. On the left is the initial seed file for Sage that we fed to it. On the right is an example input generated by Sage after 7 hours and 36 minutes, which shows the bug in action. Like you run the code on this particular input, it will crash, and it crashes at the place that has the bug. This particular bug only exhibits if there's two so-called ANIH records. So on the left-hand side, you can see we've highlighted the little list record type. And on the right-hand side, it's been changed to an ANIH. And you can see there's another one up at the top. So Sage was able to figure out that, oh goodness, there's the code is looking for this ANIH record, synthesize a new test case that has two ANIH records, and that was what was required to show the bug. And you can see that just randomly testing, you'd have a 1 in 232 chance of coming up with such a bug. But I want to show you something that I think is even more interesting, and that's what happens with running Sage on a particular media file format, starting with 100 0 bytes. So this is our initial input, 100 0 bytes. We then generated a lot of different test cases, but one of those different test cases had this RIFF at the top. So Sage was able to figure out that the program was comparing the first 4 bytes to RIFF and generate a new test case that makes that particular condition true. And then that generated several more test cases, one of which had the particular file type, and so on and so forth. Through the different generations, Sage discovers more about the different parts of the program that are looking for different parts of the input file. And here, after 10 generations, Sage generates a new test case that actually crashes the program. Now, what's interesting, after only 3 generations from a well-formed seed file, there's an actual playing media file, you end up with the same sort of crash, which shows that even though Sage was able to come up with the structure of the input, still, again, the choice of the seed file makes a big difference. So for the rest of the talk, I'm going to talk a little bit more about SmartFuzz, which is the implementation of these ideas I've worked on at Berkeley. This uses the Valgrind framework for binary instrumentation, which runs on Linux programs. It uses the STP solver from Stanford, although we've now actually generalized it to use Z3 and a couple other solvers. And it's available in SourceForge. You can download a virtual machine with it pre-installed if you want to run it. And it's on sourceforge.net. But the first thing I want to talk about is both of these tools now scale to real programs with millions of instructions per trace. So these are 2 tables that show you the source lines of code, where applicable, and the number of x86 instructions in a typical trace. So you can see here both SmartFuzz and Sage now handle code with hundreds of millions of x86 instructions per trace and perform this kind of looking for constraints, generating path conditions, and then solving the path conditions. I'm going to talk to you about some experiments I did with SmartFuzz, where I took 6 Linux programs. I took 3 seed files each. And for each program, each seed file ran 24 hours with this tool and 24 hours with Zuff, which is a black box testing tool that's roughly comparable to the file fuzzer used here in Microsoft. And I used the Amazon Elastic Compute Cloud to run these machines over about 50 different instances over a weekend. So Amazon is great because you can check out a machine with 2 gigs of RAM for 10 cents an hour, or 7 gigs of RAM for 40 cents an hour. So you can really just sort of summon lots of machines to do your bidding and then put them back when you're done. So you don't need a cluster anymore to do this kind of work. And the interesting thing about this, of course, is that both of these techniques, both the white box fuzzing and black box fuzzing, give you millions and millions of test cases. So you have to figure out how do we sort of pan through all the different test cases for the few ones, the few flecks of gold, which exhibit bugs we didn't know about before, which are high value and which are worth fixing. In other words, how do we find the right tests? So for Linux, my answer is to use Valgrind's memcheck. This is a tool that checks the execution of your program for memory safety violations. Things like memory leaks, writing the memory you shouldn't be writing to, reading memory you shouldn't be reading from, uses of uninitialized values, a whole passel of other properties you probably don't want violated in your particular program. But you can, of course, use your favorite bug oracle. So if you like App Verifier, you can use that. Or if you have any other things you like using, you can use that. Yes?
Do you recommend using memcheck with a maximum precision, or?
Memcheck only has 1 level of precision, really. And so it does have a slowdown. So the question is, what level of precision do I recommend using memcheck with? And the answer is there's really only 1 by default. And that's the one I've been using.
What is the slowdown?
It's about 2 to 5x. Does that answer your question? So the question is, what does App Verifier do? And the answer is App Verifier, it's a plugin architecture. You pick what to do. So in the experiments I did when I was here, we looked at the electric fence sort of mode of App Verifier, where it puts a guard page either before or after a particular memory object. That was the main thing that I used App Verifier with when I was here.
I guess I was asking, was your experience with Valgrind that it gave you more precision in your checking compared to the solutions at Microsoft?
So the question is, does Valgrind have more precision in its checks than what I had at Microsoft? So the answer is, Valgrind is roughly comparable to TrueScan in what it's looking for and the precision it's looking for. App Verifier is less precise and looks for less. But on the other hand, App Verifier is a much less of a slowdown for the checking. So App Verifier is almost unnoticeable, whereas this is a 2 to 5x slowdown. Does that answer your question?
Yes.
Yep.
So related to the 2 to 5x slowdown, so the traces you generate, especially if there's non-determinism in the program, are you really kind of checking paths that occur in practice, or are you checking kind of paths that you perturb? I mean, it's still valuable to find bugs,
right?
But are you finding the bugs that are likely to occur in the wild?
So the question is, am I finding bugs that are likely to occur in the wild? And the answer is, for the security testing regime, I don't care, because an adversary, if he finds any of these bugs, is interested in them. But for sort of a more reliability perspective, I don't think these are going to be good exemplars of bugs that we would find in the wild by random people using them. Does that answer your question? So The other nice thing about Valgrind Memcheck is people understand in the open source world about Valgrind. They've seen it before. It's been around about 5 years. So when you report Valgrind test cases to people, they actually fix them, which is really nice. So I was lucky enough to have 9 undergraduates for 8 weeks as part of a team of mentors. And we got them to do a project comparing both Whitebox and Blackbox fuzzing. You can see them here. And you can't really read it, but their T-shirt says we found 1,124,452 test cases with at least one Valgrind error, and all we got was this lousy T-shirt. Does that really mean we found 1 million bugs? Well, no, okay? So there's this problem of bug bucketing, which it turned out to be a rather serious problem during this summer work. The issue is there's a many relationship between test cases and bugs. One particular test case, especially if something as precise as TrueScan or Valgrind Memcheck, can actually exhibit multiple bugs because the first bug you see may not crash the execution of your program. At the same time, it could be the case that you have one sort of semantic bug which is exampled by multiple test cases. And in our experience, developers get very angry with you if you report duplicate bugs. And we were principally reporting to the MPlayer software project, which is an open source media player that ships with major Linux distributions. And the thing is, we're just posting bugs on their Bugzilla and saying, hi, you don't know us, but you have an invalid write bug you might want to look at. And the thing is, it was this interesting sort of interaction where they would fix these bugs, but they still had no idea who we are or why we were doing this until much later after the conclusion of the project. So I want to talk to you about how do you actually bucket these bugs. So this is the first thing I tried. It's called stack hash. This is the actual GDB backtrace from a real test case that we synthesized, sent to the MPlayer developers. In bold, you see the actual instruction pointers in the stack trace. And the first thing to try is, well, I have a hash function floating around. Let me just, put these in order, feed them to a hash function. This is a bug bucket ID. In essence, I'm saying up to the collision resistance of the hash function, 2 bugs are the same if and only if they have the same stack trace. This turns out it has a lot of problems, actually, but the main one is that it doesn't work. And I know that because we use it as our main approach for bug bucketing during the summer work I mentioned, and we actually had about 9 to 10% duplicate rate. As in, the developers looked at our bugs that we reported and said, oh, look, that's a duplicate right there. What was interesting here is we actually had the students sort of concurrently reporting things too. So they really did rely on the stack hash as their duplicate detection method. So what I do now, and I don't say this is the end-all and be-all, but I'll talk, yes?
Did the hash reduce your bug count from 1 million to 100, or is there other stuff going on?
Oh, the students were choosing which bugs to... So the question is, did the hash reduce the bug count from 1 million to 100? The answer is no. The students picked which bugs to report. We had 9 students. We told each of them to report at least 10 bugs by the end of the summer. So we ended up with 110 total. Some students were more industrious than others. Does that answer your question? Okay.
So did they just pick randomly, or were they given some criteria? How do you reduce from 1 million to 10 that you as an undergraduate decide to report?
So the question is, how do you reduce from 1 million different bugs to the 10 that you as the undergraduate decide to report? Well, first of all, we actually use the stack hash in order to say, okay, here are distinct buckets. So the 1 million is before any bucketing whatsoever, right? So the undergraduate's got to say, here are the different buckets, which is much less than 1 million, like several orders of magnitude. I don't have the numbers in front of me, but it did significantly reduce the number. And then the next question is, okay, did we give them criteria? Well, we told them to look for read and write, invalid read and invalid write, and prefer to report those because those bugs are more serious. But beyond that, we didn't give them any particular criteria for reporting. Does that answer your question?
Yeah, I think so.
Okay. So what I use now is this, what I call a fuzzy stack hash. And this is motivated by the fact that in the kinds of programs I'm testing, I actually have access to the source code. I can compile with debug symbols. So one problem I noticed when we were doing this work is that the code changed quite often. So MPlayer in particular at one point was updating about 4 times a day while we were doing this work. Developers of the MPlayer project really, really want you to report against the most recent version of the code, or they reject your bug report out of hand. So we have to recompile MPlayer all the time. If there's a small, tiny change to the source code, that actually leads to possibly a very big change in the instruction pointer. And so what would happen is that we'd have different looking stack traces because the instruction pointers would be different, and then report the duplicate bugs. So the approach to get around that is by using the line of code and the file the function is in instead of the instruction pointer. And then to be robust against small changes, look at all but the last digit. Now, of course, if it's only a single digit, you take just a single digit. Another issue that I observed was you have a buggy function that's called in multiple contexts. Each context is a new call site, is a new stack trace. But they're really semantically the same bug underneath. So in order to address that, the fuzzy stack hash I use now looks at just the top 3 frames of the stack trace, not the full stack trace. Yes?
Why don't you fuzz the line number instead of looking at what the line actually has, the contents of the source line?
So the question is, why did I take a sort of a fuzzy approach to the line number instead of looking at what the line actually has? Because the answer is I wanted to be, at the time, first of all, I didn't think about what you just said, looking at what the line actually has. And second of all, just coming up with an idea on the fly for why one might prefer one over the other, this would also let you handle things that are slightly different about the line. Like if there's a Oh, great, thank you. Thanks for saving me time. I appreciate it. So,
sorry, related question.
Yes.
Why didn't you use the relative offset from the beginning of the method, which is...
Right, so the question is, why not use a relative offset from the beginning of the method? And again, I didn't think about doing that. That would be...
That's pretty safe with all kinds of other reasons.
Right, and in particular, the relative offset from the beginning of the method wouldn't require the same level of debug information as I have here. Right. So as I said, I don't believe this is the end-all and be-all. It's a sort of a starting point for future work. And what's nice is I actually have a data set now, if anyone wants it, about which bugs were marked as duplicates and which weren't. So you could imagine going back and redoing this with a different approach for bucketing. So what I'm going to and then what we did in addition is built a sort of a front end for collecting all of these different bugs called metafuzz.com. This is a live website. You can go there right now if you want to. And it shows you the stack hash, the bucket ID, the particular program that was tested, and a link to download the test case. So the students use this to sort of browse through different bugs that they might want to report to developers. And developers use this to sort of download. We were able to provide links to specific test cases that they could then use and download and try out the particular bug on their own code to see if it could reproduce. And we've been adding features for reproducing the most recent version of the software and so on and so forth. So what we found in those experiments, remember I talked about those experiments, 6 programs, 3 test files per program, XUF, random testing, SmartFuzz, Whitebox testing. We found that they find different bugs. So overall, we found 19 bugs that they both found. And the reason I talked about a fuzzy stack hash is that when I say bug here, I mean bucket under the fuzzy stack hash. Okay? So that's why I went through that to talk to you about what that is. So we have 8 bugs that SmartFuzz found that weren't found by the other technique, 31 the random technique found that SmartFuzz didn't find, and 19 in the intersection. So if you break it down, this table shows that we found bugs at 5 out of 6 test programs. The numbers on the left are SmartFuzz, numbers on the right are XUF. And in 2 out of these 6, we ended up finding more bugs than the random technique using SmartFuzz. At the bottom, you have the cost per bug billing at the Amazon EC2 rates as of February 2009. So what this says to me is, of course, you want to try using both techniques, but you don't know ahead of time whether your program will be one where SmartFuzz would be better or XUF would be better. And in particular, the gzip, which is a decompression algorithm that's used pretty widely, SmartFuzz found 2 bugs and XUF found nothing. So I'm still trying to figure out exactly why those bugs are the way they are. It's a very optimized code base. It's very fun to read. But this tells us about how the relative effectiveness of these 2 different types of bugs. The other thing, too, I want to point out is, remember I talked about bug-seeking queries, where we solve for particular kinds of properties that might correlate with a bug. So this is showing us how many queries over all the runs we had of particular types, how many of them succeeded. So this gets back to the question about solving the queries. So this tells you roughly how many of them succeeded. We had a timeout of about 5 seconds for each query. And then of those, how many bug buckets came from each particular type of query. So you can see here we actually were successful in using them to find bugs, and the signed-unsigned property was the most successful out of all of our bug-seeking queries. Yes?
Can you elaborate a little bit about these three bug categories, sign, underflow, and sign overflow, sign and sign? These are not necessarily bugs, or are they?
They're not. So what happened is, so Patrice's question is, these are not necessarily bugs. We have an overflow and underflow, as I argued earlier. What this table is showing you is we created a new test case from a property whose name is here. We're trying to force an underflow, force an overflow, force a signed-unsigned conversion. And then Valgrind memcheck told us the resulting test case had an error, and then we applied the fuzzy stack hash I discussed earlier.
And the error was not the overflow itself, something else.
It was something else. So it's an invalid read, invalid write, something like that. So again, you can see that these techniques work and that the signed-unsigned found the most number of bug buckets out of all the techniques we tried. So the way I see this is a story where we had a beautiful theory, which we showed us the way to a new method of testing software. And the work that we've been able to do takes this beautiful theory and puts it into practice with scalable, practical tools that have made a real difference in the way that people test software. So going forward, yes?
So, question about the methodology. So the traces you start with, do you require those to be collected from the beginning of the program and you give it the input, or can I, in the middle of a program, look up something, collect a trace, and then use your techniques?
So the question is, can I start collecting in the middle of a program execution and start symbolically executing? The answer is not with my current infrastructure. My infrastructure uses Valgrind. Valgrind requires loading the program. And the reason for that is that Valgrind actually takes over the duties of the program loader. So Valgrind actually sets up in the same address space as your guest program room for its own host code, which does the dynamic binary translation, and then does the recompilation into x86. And it is not supported this time to attach to a running process.
Then will you end up just finding kind of bugs in the startup of programs? Because, it takes a while to generate a trace and it runs slower and so.
So the answer is, will I only find bugs in the startup of programs? The answer is, I don't believe so, because what happens is we only look at the constraints from parts of the program that depend on the initial input. And so different inputs that exercise different parts of the program will lead to different constraints and then different bugs. Especially, think of a media player program. MPlayer supports 15, 20 different file formats. The bugs you find from the MP3 playing are different from what you find from the WAV playing, or different from what you find from the AVI playing.
I'm thinking of maybe some overflow bug that the program really needs to run for a length of time to kind of exhibit.
Right.
You're probably not going to find those kind of bugs.
That's true. And so that's why I've been talking to people about checkpointing approaches for trying to save the state of the initial part of the program. So for instance, I was just speaking with Gene Cooperman at Northeastern University. He has a checkpointing approach he thinks could help with this. Yes?
There's a very large number of 16-bit conversion possible errors there. Where do they come from? If it's Microsoft, I would say they come from the 16-bit world, but where do Unix programs have 16-bit data types?
So the question is, where do Unix programs have 16-bit data types? I don't have a great answer for you, because I haven't gone back and traced all those back to the original source code, but my gut feeling is that MPlayer might have that in the particular file types we're looking at. Yes?
I wonder if you could contrast this with Clee from Stanford.
Right, so the question is contrasting with Clee. So first of all, it's a different focus. Clee is focused on very high code coverage, but they're looking at smaller programs. So they do things like they want to actually keep all of the programs stay in memory, and then they use a fork to try to go down different code paths. Whereas I actually do just a single trace at a time, and then I try to focus on larger traces. So I look forward to the day where we can take some of the things they're doing and some things I'm doing and do really high code coverage of really large programs. It's just their main difference is their focus is on getting 99% coverage of grep. And my main focus is on finding bugs in MPlayer. Beyond that, there are lots of other sort of smaller differences that we could go into according to my understanding of Clee. But, or I can tell you more about the internals of this, but I think that might be best done after the talk. Does that answer your question? Thanks. Okay. So going forward, we now know how to create more bugs than anyone will ever be able to fix unassisted. What do we do to fix these more effectively? And stepping back a bit, we now have this amazing ability to check out hundreds of machines and use lots and lots of information about the code base we're working on. How can we use that to help a programmer write better code more interactively and more immediately than our current techniques? And that's sort of one of the directions I'm really interested in, is this part of the cycle where we report and fix. For example, there have been techniques developed here at Microsoft and other places for worm defense, which try to synthesize patches immediately, given an example of a worm that exploits a particular piece of code. Well, how does that change if we go into this regime where we have a lot of time to create a patch, but the quality has to be higher because human beings have to maintain and understand it? So that's an example of a sort of a case of a direction I'm interested in going in the future. And with that, I thank you for your time, and I welcome your further questions. Yes?
After you think you fixed a bug, can you tell the tools to re-emphasize stuff that may be related to the bug you just fixed?
So the question is, after I fix a bug, can I tell the tool to emphasize a particular piece of code? So my work does not currently allow you to say this particular function is interesting, but you can rerun the tool with the test case it generated earlier on and expand around that particular path and look for bugs in the patch to the original problem. So yes, I can do it, but no, I can't do what I would really like to do would be able to say this particular line of code needs to be exercised quite a bit. Does that answer your question?
Like, how do techniques like this one scale to like more interactive programs or networking protocols, for instance? Like so when you specify test cases, this is like the program taking one input and then running with it all from start to end, or you can also do like, supply an input, program does something, then supply another input, program does something, supply another input. Kind of testing as well.
Right, so the question is, what about interactive programs or protocols, right? So my work that I show you doesn't work on that. There has been other work that's been done here at Microsoft that does look at that. And I'm talking to some people in the networking group at Berkeley about how to look at that particular issue. In principle, what you need is a proxy that can let you replay protocol dialogues and sort of close the entire environment to let you treat the input to the whole program as the entire dialogue between one server and one client or what have you. In principle, it's possible. It's just it has to be done, and there's some different questions that come up about how to search the state space. Does that answer your question? All right. Thank you for your time, everyone.